In this video, we'll talk about how different containers can communicate with each other and with standalone applications on the same host. Additionally, we'll explore communications between containers located on different hosts. We'll cover all the default Docker network drivers, including bridge, host, overlay, and others, and discuss when to use each specific one. I'll also provide some hands-on demos that you can reproduce on your own. We frequently use Windows and Mac for local development. We may build and run multiple containers on a laptop, while some network drivers, such as Bridge Network on Mac, may still work. They do have some limitations. For instance, on Mac, Docker is created inside a virtual machine, and while on Linux, you can access a container using its IP address directly. It's not possible on Mac. You would need to forward ports to the local host in order to access application. Now, some networking features of Docker can still be applied for local development, but most of them are used for running applications that are accessible by external clients on, let's say, a remote Linux server. So it's important to keep in mind that there are two different use cases for Docker and networking. You may be wondering why not to use Kubernetes to run applications in production. Well, perhaps you only have one or a few applications to run on Linux, and deciding to run those apps in Kubernetes can lead to significant overhead. Kubernetes is a distributed system and needs to run many different services such as kubelet, DNS, etcd, and different controllers. And you need to spend a lot of time maintaining and upgrading your Kubernetes clusters. The typical example is that you may have a standard 3-tier application. You have clients such as web browsers or maybe mobile applications. There is a logic tier with your application, and for the data tier, you may have a relational database. You can run your app and the database on the same Linux server using Docker, which is perfectly valid use case. Don't use Kubernetes unless you really have to. If you want to get the most out of Docker networking, you need to use Linux. Let's start with a default bridge network, which is used whenever you start a container. But first, let's take a look at what a bridge is in a regular network without Docker. In a nutshell, a bridge is a physical or a virtual device that connects multiple local area networks. Let's say you have a large number of devices connected to the local network in an office building. Maybe you have 30 devices, like computers, printers, etc. Now, when two or more devices on the same network try to transmit data at the exact same time, this will lead to a collision, and some packets will be dropped. So the more devices you have connected to the same network, the more collisions you would have. This reduces performance of a network, since if the packets are dropped, the sender needs to resend those packets. And we say that all those devices on that network segment belong to the same collision domain. In the early days, to solve this problem, the bridge was introduced. The bridge can divide the local network into multiple smaller networks. For example, we can split the original network with 30 devices into two networks with 15 devices each. And each network will get its own collision domain. Fewer devices on the network mean fewer chances of a collision to happen. Now, when it comes to Docker, the two segments that the bridge connects are your local host, it can be your laptop or a Linux server where you run your containers, and the virtual network created by Docker. For example, when you install Docker for the first time, it will create a default bridge network with CIDR like 172.17.0.1/16, and all containers that you create on that host will get IP address from that range. Also, containers that are created in the default bridge network will be able to communicate with each other. Now, the default bridge network has some limitations, and even Docker itself does not recommend using it, especially in production. The recommended approach would be to create a new user-defined bridge network. The biggest difference you'll notice immediately is that with a user-defined network, you can use DNS to send requests to your containers. This applies only to communications inside the bridge network between containers. You still won't be able to use the container DNS from the host. The name that you give to the container when you start it will become a DNS name. This is not possible in the default bridge network. Alright, let me run a quick demo for you. First of all, let's list all the default networks created by Docker. We have bridge, host, and none. Now, we can use inspect subcommand to get all the configurations for a specific network. For example, the default bridge network has a seeder 172.17.0.0/16 and the gateway.1. Additionally, you can see the driver that was used to create this network. Let's go ahead and run the first container. By the way, I have the source code and all the commands in the README file. You'll find a link in the description in case you want to follow along. Now, to run a container, we need to specify the image. I have built one for both AMD and ARM architectures, and it's public, so you can copy, paste, and run exactly the same command. Use -d to run it in the background. On a Mac, I have to explicitly forward ports to localhost in order to access the application. For example, if you run Docker on Linux, you can directly access the container by its IP address from the same host, of course. For Mac, I'll map port 8081 on localhost to port 8080 inside the container where I run Python application. To get all the running containers, you can run docker ps. In case your container has failed, you can add -a to get all containers, including those that are stopped or have failed. Well, to get more information about the container, we can also use inspect subcommand. So you can see the container got its IP address from the default bridge network, which is 172.17.0.2. On Linux, you can directly hit this IP with curl. On Mac, I have to use localhost. Let's send a request to the container. The Python application will return the hostname and the IP address of the container. Alright, now let's run the second container. It's exactly the same process, except we'll give it a different name and port forward to a different port, 8082. Alright, so far we have two containers, my app and my app v2. We can use curl to access both of them. Now, let's verify that both containers can communicate with each other. We'll SSH into one of the containers using exec command, and -it stands for interactive shell. Since these containers are based on Alpine Linux, we don't have bash, so we need to use sh shell. Let's use curl to access both containers by using their IP addresses. This way, we can access the same container and also another one using their respective IPs. However, ideally, we would want to use DNS to send requests between containers. Let's try that with curl. Well, that's the limitation of the default bridge network. DNS is not supported. Before we continue, let me remove both containers. Now, let's go ahead and create a custom user-defined network. We'll name it MyBridgeNet, and though it's totally optional, you can provide a seeder and a gateway. List all the networks and you'll find the new bridge network. Let's go ahead and inspect it. As you would expect, you'll see the provided subnet and gateway. Since it's a virtual network only accessible from the host, the seeder you use doesn't really matter. I would even suggest letting Docker choose the seeder for you. Now, in order to create a container inside that network, we just need to specify the network. It's as simple as that. The rest stays the same. Let's also create the second container in the same network. Well, now we can access both containers using curl, but you'll notice that the IP addresses come from the seeder we specified earlier. So we have 10.0.0.2 and .3 as IP addresses. Again, let's SSH into the first container. And now we can actually use DNS. The DNS will be the same as the name of the container you created. This is the biggest difference and a key reason why you would want to create a custom bridge network instead of using the default one. Alright, let me clean this up by deleting the containers as well as network. Now, most of the time when I need to create containers locally, I use Docker Compose, which is a declarative way to define which containers to run. This compose file does exactly the same thing as what we ran before. We declare to run my app and my app v2 containers. By the way, those are DNS names that you can use inside the network. We also declare exactly the same bridge network and optionally provide a seeder. So this is exactly the same setup, but it's defined in the single YAML file. Now, in order to run it, just execute docker compose up command. Use -f to specify the compose file and -d to run it in the background. We can test it with curl in the same way. And finally, to tear this down, just run docker compose down. It will shut down the containers and remove the network. The next networking mode available is called host. If you use this option, your container will not get its own IP address and will share the same networking namespace as the host where you run the container. Essentially, there is no networking isolation from the host, and it would appear as you were running a regular application on that host. Therefore, any application running on a different server will be able to access your container using the host's IP address. This networking driver only works on Linux instances and is most likely used in production to expose your services to clients rather for the local development. When you use host network, obviously you cannot use or bind multiple containers to the same port. For example, you won't be able to run two proxies on port 80. Now, when using the host network, it does not require address translation NAT, and no userland proxy is created for each port, which means it increases performance. So the two main reasons why you would choose this option are to optimize performance and if the container is using a lot of ports that you need to bind to the local host. Now, to run the demo, we need to use a Linux box. For example, I'll use Ubuntu. I have two virtual machines here, both with Docker installed. Let's go ahead and create a Docker container on the virtual machine using host network for the container. When you start a container, it will bind to port 8080, which is used by Python internally inside the container. Next, let's get the IP address of that VM. And now, from the second virtual machine, let's try to access the container. Alright, it works. If you're following along, don't forget to delete that container. That's all for this demo. My point was to show you that the container, which is using the host network and two other applications, it will appear like any regular application running on that virtual machine. The next type is none. This completely isolates the container from the host and other containers running on that server. When you use this option, only the loopback interface will be created for the container. You won't be able to publish or forward any ports. This mode can be used, for example, to run batch jobs or some kind of data processing pipelines. For the demo, I'll use Linux as well. On other platforms such as Mac and Windows, Docker may create additional network interfaces inside the container. Let's go ahead and run the container, specifying none for the network. Now, let's get all the network interfaces in that container. You can see that only loopback interface is present. This means the container is totally isolated from the host and any other containers that may be running on it. That's all for this demo. Traditionally, to expose a container to the outside world, we used a bridge. It works just fine, but adds additional complexity. Besides the performance penalty, since the packet needs to go through additional hop, we also have to map ports from the container to the host in order to expose it to other applications. Now, IPvlan is a new network virtualization technique. It's extremely lightweight since it does not use a bridge for the isolation and is associated directly with the Linux network interface. As a result, it is easy to provide access for the external facing services, and there is no need for port mapping in these scenarios. When you start a container using this type, the container will receive IP address from the same CIDR range. For example, if my host has IP address of 192.168.50.55 and it's on /24 network, this means that the range starts from 50.0 and the last IP address for this range is 50.255, which gives you 256 IP addresses. Now, the container may receive 50.2 IP address. Any service on that network will be able to access your application using that IP address, whether it's a VM or another container on a different host. And the traffic will be routed using the network gateway. For this demo, I'll use two Linux VMs. On one, I'll attach a container to the Linux network interface, and from the other one, I'll try to access the Python application. First of all, let's find the parent network interface by running this command. Let's take a note of it. My interface is ENS33. We also need to note the host's network. We'll use it in the next step. So the IP address is .55 and we have a network of 192.165.50.0/24. Alright, the next step is to create a network. Don't forget to update the subnet and gateway values. The gateway IP address is the first usable address in that range. Also, don't forget to update the parent network interface. Now, let's make sure the network is created. Let's start the container on the first host. Remember to specify the network and note that you don't need to map any ports. Next, let's find the IP address assigned to this container. And from the second host, which is in my case another virtual machine, we can use curl to test the application. Alright, it works. It's a simple demo, but in the near future, I'll create a detailed tutorial covering new Docker networking techniques. Some applications, especially legacy applications or applications which monitor network traffic, expect to be directly connected to the physical network. In this case, you can use Macvlan network driver to assign a MAC address to each container's virtual network interface. It will appear as a physical network interface directly connected to the physical network. The difference, for example, between IPvlan and Macvlan is that if you use IPvlan, your container will get the same MAC address as your host, but in case with Macvlan, the MAC address will be different. Similar to the previous demo, we need to find the network interface that we want to use for Macvlan. It's going to be the same ENS33 interface, so take a note of it. Now, let's create the network. It's very similar as well. You specify the subnet that the host uses, the gateway, and the parent network interface. And of course, you choose to use the Macvlan Docker driver. But before we create this, take a note of the MAC address assigned to the virtual machine's network interface. List all networks. Next, let's run a container in that network. Let's inspect that container. You'll find that this container has a different MAC address than your VM. In the case of IPvlan, the MAC address will be the same. We can SSH into the container and get all network interfaces. Just to prove my point, you can compare the parent MAC address with the MAC address created for the container. That's all for this demo. Now, when you deploy your application to production, of course, you will need more than one physical or virtual server, each with a Docker daemon installed. The overlay network driver creates a distributed network among multiple Docker daemon hosts. This network sits on top of overlays, the host-specific networks, allowing containers connected to it to communicate securely, especially when encryption is enabled. Most frequently, this type of network is used with Docker Swarm. However, it is also possible to connect individual containers as well. In my opinion, if you really want to manage your containers at scale, especially in production, you should consider using Kubernetes. Most people use overlay with Docker Swarm, but in this demo, I want to show you how to connect individual containers to the overlay network. Well, for this demo, I also have two virtual machines based on Ubuntu. Before we can run the demo, I found that many people face the same problem with the overlay network, and we need to disable something to make it work. Let's find the network interfaces on both VMs. So in my case, it's ENS33 on both VMs. Now we need to disable this on that network interface on both VMs. This solution is not persistent across restarts, so you would need to maybe create a script and automatically run it on boot. There are many options available for you to solve this. Even if you want to connect individual containers to overlay network, we still need to initialize the Docker Swarm. It's actually very easy. On the first VM, just run Docker Swarm init. Then it will give you a command that you can execute on other VMs to join Docker Swarm. Keep in mind that each VM should have Docker installed. So far, we have a manager and worker node. On the manager, let's create overlay network. Add attachable flag in order for individual containers to be able to use this network. Otherwise, only Swarm services will be able to use it. Check if the network was created. Now, on the manager node, let's start the container and use this overlay network. If you list networks on the second worker node, you'll notice that the overlay network is missing. It's automatically created when you start the container that uses that network. Let's go ahead and run a container on the worker node. Now you can see that the overlay network is created. To verify that we can access containers on that overlay network deployed on different VMs, we can SSH to the second container and use curl to send a request to the first container on the manager node. I have a lot of tutorials like this on my channel covering Kubernetes, databases and other infrastructure components like Kafka. If you like it, consider subscribing to my channel. Thank you for watching and I'll see you in the next video.